In this lesson, we will be evaluating logarithmic functions and graphing logarithmic functions. First, what we want to do is look at logarithms. Logarithms answer the question, how should we solve a problem like 2 to the x equals 6? Now, what logarithms do is they undo the exponential. So if we have a problem like 2 to the x power, we want to undo 2 to the x, so we take the logarithm. We take the logarithm of each side, log of 2 to the x equals log of 6, because we want to take the same thing to each side. Now, if you remember from our parent functions, we have b to the x power. B was our base. Same thing, same idea here. If we have a base of 2, we want to take log base 2 of 2 to the x. These two things are inverses of each other. They'll cancel out. We're left with x. X equals log base 2 of 6. So these two equations are equivalent to each other. Okay, if we look at the definition, just as I said before, log base b of y. We're not multiplying these two things together. This is actually a function. Log base b of y equals x. And again, these two are equivalent to each other. If we take a look at a couple examples, I just want to remind you that our exponential function was b to the x equals y. Our new function is log base b of y equals x. So if we take a look here, it says rewrite in exponential form. This question says 2 to the what power equals 32. Okay, 2 to the what power equals 32. And we already know the answer is 5, so if we write it in exponential form, 2 to the 5th power, I can make my mouse work here, 2 to the 5th power is 32. Okay, so over here, 10 to the what power equals 1? Well, we know that 10, or anything to the 0 power equals 1, so 10 to the what power equals 1, the answer is 0. 9 to the what power equals 9? We know that anything to the first power equals itself, so the answer is 1. 1/5 to the what power equals 25? Well, if we were to look at it this way, we know that 5 squared is 25, and from lessons that you've done before, we know we can just swap that around, so 1/5 to the -2 power also equals 25. So the answer here is -2, and this is how you would write it in exponential form. These ones, they just want us to evaluate it ourselves. So 3 to the what power equals 81. And this may require some guess and check, so if you need to take out a calculator, that's totally fine. Just plug in some values. Eventually you'll find that the answer is 4. 3 to the 4th power is 81. So our answer is 4 there. This one is asking 1/4 to the what power equals 256. Again, with a little guess and check, if you don't know right off the top of your head, we know that 4 to the 4th power is 256. So taking some inverses again, if we were to flop that around, we get 1/4 to the -4 is 256. So our answer here is -4. Next question. 10 to the what power is 0.001. These ones I kind of like to look back at scientific notation, but you can do it the way we have been doing it. Since it is a decimal, I'm just going to say 1, 2, 3. Oh, we have to go back 3 spots. 10 to the -3rd power is 0.001, so this answer is -3. Lastly, we have log base 64 of 2. 64 to the what power equals 2. We want to notice that since the number is getting smaller, this is a root. So 64 to the what power, what I like to do is make a factor trade. This helps me figure it out a little bit faster. We have 8 and 4, 2's here, 2 and 4, 2 2's here, 1, 2, 3, 4, 5, 6. We have 6 2's. So 2 to the 6th power we know is 64. And since we know that it is a root, 64 to the 1/6 power equals 2, so our answer is 1/6. Moving on. A couple of vocab words here. Common logarithm is a logarithm with base 10. If you see something that looks like log of x, that is the same thing as saying log base 10 of x. That's what the common logarithm says. If there's no base written, that's because it's base 10. And that you'll find on your calculator if you see a little log button. That's if you calculate log base 10. So don't freak out if you don't see a base here. That's just saying log base 10. Okay, and then natural logarithm is a logarithm with base e, commonly written as ln. So if we have an ln of x, that is the same thing as saying log base e of x. These two are equivalent just like these two are equivalent. You also have an ln button on your calculator. Okay? So let's look at some inverses now. We know that the logarithmic parent function is log base b of x, and the exponential parent function is b to the x. These two are inverses of each other. And to prove that, we're going to do the composition. So if you were to plug f of x into the g of x equation, you would get log base b of b to the x. These two are inverses of each other. They're gone. We're just left with x. Same thing over here. If you were to plug g of x into the f of x equation, we would get b to the log base b of x powered. These two are inverses of each other. They cancel out. We're just left with x. Please, please, please be careful. These bases absolutely must be the same in order for them to cancel out. If this was like a v or something, or that's, I guess I should say k, because b and v sound the same on a microphone. Log base b of k to the x, no, can't do it. Has to be the same base, okay? So once again, logarithmic functions and exponential functions undo each other if they have the same base. Okay, some more examples. 10 to the power log of x. Oh yeah, okay, so we know that this is base 10, right? Good. So 10 to the log base 10 of x. Those two things cancel out. We're just left with x. Not so hard. Over here, uh-oh, we don't have the same base. But what if we rewrote 125 to have the same base? We know that 125 is the same thing as saying 5 to the third power. So this 125 to the x is actually the same thing as saying 5 to the third power to the x power, right? So now we have log base 5 of 5 to the 3x, right? Because if you take this to the x power, it's just like multiplying them. So that's what we're left with. And now we have the same bases. We can cancel those out. We're left with 3x. Now we're going to try it out and find the inverse function. So if you remember from the definition, you should be able to just see what the inverse function is on this one. But just for good measure, we're going to calculate it out. To find the inverse function, we switch the x and y. So in this one, we get x equals log base 8 of y. And since we have a base 8 here, we want a new base 8, and we bring everything else up to the power. Log base 8 of y. These two are inverses of each other. They cancel, so we're just left with y equals 8 to the x. Notice what I said earlier, if you were to just look at the definition, this is our b to the x. So if it's something simple like this, you can just notice right away that that's our inverse function, 8 to the x power. Okay, and for this one, again, to find the inverse function, we switch x and y. So we have x equals ln of y minus 3. To solve this, we remember that ln is the same as log base e. So now we have a new base e to take the opposite of the ln, y minus 3. E to the ln cancels out. They're inverses, so we're left with e to the x power equals y minus 3. Simplify that, bring the 3 over. We're left with y equals e to the x power plus 3 is the inverse function to this equation right there. Okay, next slide. This is just showing you a little bit of the geometric side of things. Remember, inverse relationships, exponential and logarithmic functions are inverses of each other, so this is just showing you on a graph that that is true. This here is the line y equals x. And if something is an inverse of something else, we know that it's going to be a reflection over the y equals x line. So if you remember in our exponential growth function, our parent function was b to the x. One of the points was 0, 1, right? So if we have 0, 1 on this side, we want to find the inverse. We swap the x and y. So down here we should have 1, 0, right? And look at that, 1, 0. So it's just a reflection over the y equals x line. And if you were to look at this one over here, it's going to be the same idea for the decay. Plot a point, it's going to be a reflection over that y equals x line. Okay, so now we're just going to graph these functions real quick. The equation for graphing our logarithmic functions is y equals log base b of x minus h plus k. Now, h and k, same thing from the exponential growth and decay, our new origin, hk. Okay, but this time x equals h is our new vertical asymptote. The domain is x is greater than h, and the range is all real numbers. Just to quickly remind you, we had in our b to the x equation, our range was the y values, and our domain was all real numbers. So again, they're just flipping them, right? But let's just forget about that for now. Let's look at our function. Y equals log base 1/2 of x plus 4. Notice that this is by itself. The 4 is not within the parentheses. Am I right? So that is a big mistake that somebody could make. Okay, we want to make sure that if there is an h, it is in the parentheses. This is our k value. So our new origin is 0, 4, right? Now what we want to do is look at the inverse function. And if you remember, this is our inverse function, 1/2 to the x power. First, what we're going to do, since we cannot calculate this, if we were to plug x values in here, we would have no way of figuring that out. So right now, what we want to do is we want to take our parent function from our inverse function, 1/2 to the x power, and plug in some values. So I took the liberty of doing so, and we've had this function numerous times before. We know if we plug -2 in here, we'll get 4, because we have to flip it around. So -2, -1, 0, 1, and 2 will give us these values if we plug it into the equation. And now we are graphing the log function. So what do we do when we have to find the inverse? We switch the x and y. Okay, so if we found our inverse b to the x, to have these, our inverse function of log, we just switch the x and y around in the table. So our b of x, which is our y, is now going to be our x values. 4, 2, 1, 1/2, and 1/4. And our old x values is now going to be our y values. Because they're inverses of each other, we are switching the x's and y's. Very important to remember that. Okay, just like before, first things first, we graph our new origin, 0, 4. Graph our new axes. We're still going to stay on the y-axis because our y value, or our x value, was 0. From here, we graph our new points. Cannot stress how important this is. Please forget about this after you've calculated that and flip them. Okay, and so first we go 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. Draw your line. Try and get through the points anyways. Okay, so if you'll notice, in this graph, we're actually crossing over the x-axis. And that is okay because this is now the log function. Before, our x was our asymptote, but now it's going to be our y's, because if you'll notice, our domain, x is greater than h, or h is 0, and all of our graph lies on this side of the x-axis, because x equals 0 is our asymptote. Okay? We have one more example. Going to run through really quick because I know you guys have already caught on. y equals log base 3 of x minus 2. If you remember, our h value here is inside the parentheses. There is no k, so our k value is 0. And h is by default negative, just like it was before, so we have a positive 2 for our h value. Positive 2, 0, our new origin. Graph our new axis here. We're going to stay on the x-axis this time because k was 0. We're not moving up or down at all. What is the parent function? Forget about 2, forget about there's no k. 3 to the x is our parent function. So first we want to look at plugging values into, arrow, into that. And once again, I've taken the liberty, -2, -1, 0, 1, 2, plug -2 in, you get 1/9. What do we do? Switch the x and y values. Switch the x and y values. I will say it a million times and a million times again. Switch the x and y values. Our old x values are now our y values. -2, -1, 0, 1, 2. 1/9. Our old y values are our new x values. 3 and 9. And we'll go ahead and graph those quickly. 1/9, -2. From our new origin, please don't forget to plot from your new origin. 1/3, -1. 1, 0. Whoops, 1, 0. Whoops. 1, 0. Was right the first time, sorry. And 3, 1. And 9, which is somewhere out here, and 2. Okay, draw a line, not crossing our x equals 2 line because that is our new asymptote. And again, we crossed over the x-axis. That is okay because we are graphing logs. Do a quick review. Logarithm with base b, log base b of y equals x, equivalent, inverse functions here, common log, log base 10, natural log, the ln, which is log base e, inverse, log base b of b to the x equals x. Because these are the same base, they can cancel out. We're just left with x. Same thing on this side, b to the log base b of x power. These are both b's, they'll cancel, we'll get just x. How do we find the inverse? Flip your x and y and solve for y. Same thing when you're graphing. First we'll look at our new origin, hk, plot points for our b to the x powers, flip the x and y, and plot those points. And that will conclude the lesson.